Okay, so yeah, today I want to talk about decadal predictions of warm summer temperature extremes. And for the sake of this work, I focused on Europe, and I also have some thoughts, or we also have some thoughts on the Northern Hemisphere in general. This is some work that I did when I did my first postdoc at the Max Planck Institute, and now I'm not there anymore, but I actually work in Paris now. Yeah. Okay, so let's get going. Why predict extremely warm summers? I think it's fairly obvious that we want to do that because extremely warm summers are very high impact events, and forecasting them in time would be of good use for decision makers to actually take mitigative action in time, possibly. However, the problem so far was that beyond the warming trend, the prediction of an extremely high summer, at least in Europe, proved pretty difficult. Now, most studies that showed decadal prediction skill beyond the trend attributed that to some degree to memory that resides in the ocean. So for Europe, a couple of studies had looked into the North Atlantic Ocean, and yeah, that's sort of the idea that was behind this study, which was that we were sort of trying to link predictions of the North Atlantic Ocean to predictions of, or the occurrence of warm summer temperature extremes over Europe, hoping to get some predictability through this link. And that's what I will be talking about today. Sort of the first step in this work was to find out if there actually is a link between the occurrence of a summer temperature extreme in Europe and North Atlantic SST. And so the first step in that direction is shown here in the map. I hope you can see my cursor. If not, I will try to describe. In the map, you can see composite differences between strong, for surface air temperature, between strong and positive and negative phases of North Atlantic SST, where North Atlantic SST is defined as area average over this gray box in this plot. Yeah, and you can see yeah, the composite differences for surface air temperature globally. So there appears to be, if we now have a look at Europe, at least in the northern part of Europe, there seems to be an influence of subpolar gyre or North Atlantic sea surface temperature on the temperature evolution in northern Europe in general. But there are also other regions on the globe that show quite a bit of a signal here. And all of this is, by the way, based on an assimilation model run with the CMIP6 version of the MPI ESM HR model, but I will get to that in a minute. So in terms of a mechanism, what could transport the temperature anomalies from the North Atlantic to these regions over land? We, for example, looked at different things, but this shows sea level pressure, again, composite differences for positive minus negative North Atlantic SST phases over time for the period 1970 to 2018. And again, detrended. And you can see that there's, you can actually really see quite a nice wave train, Rossby wave train-like feature in these sea level pressure differences that propagates to Europe, but then also continues sort of to propagate further downstream to Northeast Asia, for example. And for the remainder of this presentation, I will focus on the three regions that are marked here. So I'll have Central Europe, or a Central Europe-like region in black, which is just there for comparison. But then two regions that are defined over the centers of action of this wave train, and the regions that also show a strong temperature signal and a connection to subpolar gyre SST. And I'm going to call these regions Scandinavia or Northern Europe and Northeast Asia. Now, to the question whether or not the an occurrence of heat extremes is linked to the North Atlantic SST. At the top right, you can see the 10-year low-pass filter time series of subpolar gyre sea surface temperature in the gray box here, in the gray line. And then in the colored lines, surface air temperature variations from the three regions that I just talked about. And whenever there's a dot, that means that there's an extreme summer. So we're looking at June, July, August averages here. And that is defined as exceeding 2 standard deviations of the respective variability. And you can see that that it appears that these extremely warm, the occurrence of these extremely warm summers seems to cluster around times where sea surface temperature is high, whereas when sea surface temperature is cold, it appears that there aren't so many extremes that occur. Now, this is all based on the model world. Again, this is an assimilation run. It can be assumed to be relatively realistic, but you could also look at observations, and that's the final plot for this slide. So this is the same plot as I just showed, but using HUD crew data, observational data, and you can see that at least qualitatively, the two look very similar. So this clustering of occurrences of summer temperature extremes, warm summer temperature extremes around warm subpolar gyre phases seems to be robust in observations as well. Now about the question to look at, or about the question of predictions. The problem with the prediction is that we usually don't have a really big sample, and what we try to do in this work is we try to maximize the sample by pooling the hindcast ensemble. And I will tell you what we did. Just briefly, here's the model data that we used. So we used the CMIP6 MPI ESM high resolution decadal hindcasts. We have 10 ensemble members that are yearly initialized in November and then run out for 10 years and 2 months. They span the time 1960 to 2018. Plus we have a corresponding assimilation run that the plots on the previous slide were based on. And then we also have HUD crew temperature observations whenever I talk about observations. Now, what do we do to maximize the sample? The fact that we actually have 10 ensemble members and each ensemble member is run out for 10 years means that after the 10th year of our predictions, so after the year 1970, we have 100 realizations available for every year. This is schematized at the bottom. So if we just focus, for example, on the year 1980, going back in time, we have 10 lead years that represent 1980, and we have 10 ensemble members of each. So that really means we have 100 realizations of every year from 1970 to 2018. And with these 100 realizations, we can try and see if we can identify extremes there. And we do that by defining a lead year dependent threshold for an extreme, which is 2 standard deviations again, as the same definition as before in the observational analysis. And then we can just count how many realizations of the respective year exceed this threshold, or these thresholds, because it's lead time dependent. So we have 10 thresholds per year. And then we can just count them, divide them by 100, and then we have a percentage that gives us the predicted probability of occurrence for a hot summer in the respective year. Okay, and now let me show, this is my final plot. Let me show you how this looks when you look at it graphically, or when you compare predictions and observations. Now this is the time series again for the observations observed summer temperature extremes in the different regions at the bottom. That's based on the first plot I showed you. This is the sea surface temperature index that we used before. And now at the bottom right, top right, you can see that I sort of added asterisks, which indicate the predicted probability of occurrence for a warm summer in the 3 regions based on the pooled hindcast ensemble, as I explained on the last slide. And we can do that for every year. And if we do that for every year, then we can see that actually across the time series, there is a bit of quite a bit of spread, but it seems as if the predicted probability of occurrence actually follows the sea surface temperature index quite nicely. So whenever sea surface temperature is high, the model predicts a heat extreme in the regions with a higher probability than when sea surface temperature is low. And we can also see that here. So this on the right-hand side is the upward pointing arrows indicate warm sea surface temperature phases, downward pointing arrows indicate cold sea surface temperature phases. And what's shown is the predicted probability of occurrence for a surface temperature extreme together with the corresponding standard deviation. And you can see that these do not overlap the standard deviation, so we can claim that there's this difference, the difference in prediction of these occurrences is significant. Now, how does this compare to observations? Again, I added them on the right-hand side, so this is just the count of observations, which you can see it's on the left side in plot A at the bottom, divided by the total amount of years. And we can see that at least qualitatively, the predictions agree with the observations. So the more heat extremes are predicted and occur in warm subpolar gyre temperature phases and in cold subpolar gyre temperature phases. And at least in the Scandinavia and the Northeast Asia region, these differences are also in observations are also significant. And that's why we claim we can skillfully predict the probability of occurrence for a warm summer temperature extreme. Okay, so again, in very brief, what I think you should take home. Extremely warm summers are observed and predicted to be more likely to occur when the North Atlantic is warm than when it is cold. And this gives us skillful predictions of the probability of occurrence for such extremes. And the second thing is more of a methodological thing, but yeah, pooling the hindcast ensemble, I think, or we think, is a powerful way to examine predictions of low likelihood, high impact events. And I encourage you all to try this out. Okay, thank you for your attention. This was published last year in GIL, so if you're interested, you can also either ask me, write me an email, or just go into the paper.